Hey, Calc students, time for another free response question from an old AP exam. The question we're looking at today is AP Calc AB exam from the year 2013, and the question is number 4. So as soon as you look at this, you can see that it's a derivative graph style question. They give you the graph of a derivative, and you're going to be using your skills with the fundamental theorem combined with geometry. Now this one's a little bit different in that it gives you a curved line, but it tells you what the areas under each section are, and oftentimes you get pieces of a linear function combined with semicircles, and you have to calculate the area with geometry. This one's a little bit easier that way, but it's a little more challenging in others. So before we do this, I want you to notice a couple things here. If you're looking at the question from AP Central, you're going to notice the graph is... it says the graph of f prime, and the graph is black because of the ink is it's just black and white. But I have written over the top of this in red because of the process by which we go in class, where the original function is black, the first derivative is red, the second derivative is blue. So what I'm going to do is draw a short example over here. And you want to be really solid with this, but I'm going to draw a little example over here that I'm going to refer to as we go through this, and eventually I'll be erasing part of this. But if you recall, and I'm going to do this one kind of small, but you always want to remember, if you have a classic cubic style function that is your original function, f, and we're going to graph the derivative. Your strategy is always going to be peaks and valleys of the original are going to handcuff to the x-axis because your slopes of your tangents, which is what a derivative is, the slope of the tangent right there is 0. So the x-axis has to be where the function crosses, where the derivative crosses, and here it's 0. So those are always where I have my zeros of my derivative. So the original function is increasing, therefore the graph of the derivative is positive there. The original function is decreasing, therefore the graph is negative, but it has to come back to this 0. The original function is increasing, graph of the derivative is positive. Okay, simple relationship, and you always want to say peaks and valleys correspond to x-intercepts of the first derivative. Then you switch to the second derivative. You treat the first derivative like an original function, and so you handcuff its peaks and valleys. Well, there's just one right here. It's a pretty beginner function. And so the red function is decreasing, therefore the graph of its derivative needs to be negative. The red function is increasing, therefore the graph of its derivative is positive. But it's the second derivative of the original. And the x-intercepts of the second derivative should correspond on the original function to an inflection point. Oops, an inflection point, which it does approximately. Okay? And what you want to do is always be comparing what are the attributes of the original function to compare to the derivative? What kind of clues are involved here? Because really the first derivative tells you everything you need to know. It tells you about concavity. It tells you about maxes and mins. And the one thing that you want to notice, and in fact you're going to need it for this one, is that sometimes the behavior of the original function doesn't just create peaks and valleys. Sometimes we have flat spots. And so I'm going to do that one. Let's see if we can sneak that one in right here. Let's pretend your original function, as it's coming up, it just comes to a flat spot, but continues to increase before it comes back down. Okay, and let's pretend that was what our function looked like. Well, when you go to do your peaks and valleys on this type of a question for your first derivative, so if this was our original function, well, you have a peak. That one's pretty easy to do. And you would handcuff that, and you could say, oh, well, yeah, I've got a horizontal tangent there. But you also have one here. It's also an inflection point, but you'd say, oh, well, I'm going to have to handcuff it there. And if you notice, the original function is increasing the entire time, which tells me my derivative needs to be above the x-axis the entire time. But at this spot, I'm positive, I'm increasing, but I hit 0. So I'm positive, but I hit 0, and I bounce off of there. It's going to create a kiss. So flat spots always create kisses on our graph. So it's going to do something like this. And it is going to hit the x-axis because it is 0 right there, but then it's going to come back up and then go back down. Now the original function is decreasing, and sure enough I'm negative. There's the graph of my first derivative. So If we cross the x-axis, those always correspond to hard peaks or valleys. But if we kiss the x-axis, it still creates a horizontal tangent, but it's just a flat spot. Okay? And then on the second derivative, once again, we treat the red like an original. We have a little peak right here. And this valley bottom is right on top of itself because it's already on the x-axis. So the blue function is decreasing to here. So since it's decreasing, the graph of its derivative is negative. The red function is increasing, so it's positive, but I have to come back down to this 0. And then the red function is decreasing, so I'm going to be below the x-axis. And that is my second derivative. Okay? So the other thing, or the last thing would be, you knew that this was an inflection point, and sure enough, it corresponded also to the x-intercept of the second derivative, and this right here would also correspond to an inflection point on the original, which it does. Okay. And so one little thing you want to notice here is that the first derivative, look at concavity. There's a big hint on the first derivative. Where the first derivative in red, where red is increasing, the original function is concave up. Where red is decreasing, the original function is concave down. So you can look at increasing and decreasing of the derivative to tell you about concavity on the original, but you look at positive or negative of the derivative to tell you about increasing or decreasing. So if it's above the x-axis, the original function is increasing. If it's below the x-axis, those are the places where the original function was decreasing. Okay? But then, where the derivative is decreasing, original is concave down. Where it's increasing, original is concave up. Okay? And the peaks and valleys of the first derivative correspond to inflection points on the original. Now, some people don't like to get that picky with the first derivative. They'd rather just draw the second derivative, and it depends on the function whether that's a decent strategy or not. But we'll see as we go. So we'll try to save these and refer to them. But now let's look at the graph they gave us. They gave us a first derivative, so that's why I overlapped this in red, and it kind of makes things a little bit easier to see. And we'll be able to get the information and right out of this very quickly, especially if we're referring to these down here. So let's see what we can figure out. And with the information, they're giving again us the areas in these little regions that are captured by the function in the x-axis and the y-axis in part of it, and even the end here, y equals 8, or x equals 8. So let's see what they say. It says the figure to the right here shows the graph of f prime, the derivative of a twice differentiable function f on the closed interval 0 to 8. Got it? One other little thing is I put in all the values on the x-axis and the y-axis. I like to clean it up a little bit. It makes it a little easier to understand and read. The graph of f prime has horizontal tangents at 1, 3, and 5. Now, it's very surprising that they actually said that, because that's something you could have concluded on your own. There's a kiss, of course there's a horizontal tangent, and there's one there, and there's one there. We actually already knew that. It was weird that they said that they were there. The areas of the regions between the graph of f prime and the x-axis are labeled on the figure. The function f is defined for all real numbers and satisfies the condition f of 8 equals 4. Okay? So we're going to need that, but we know that f of 8 is equal to 4, so I'll just put that here. F of 8 is equal to 4, and we'll see when we have to use that. So part A says, find all values on x in the open interval in which the function f has a local min. Justify your answer. Well, this is actually a very easy question, but let's go down to this example here. See how we had this minimum on the original function right there? That minimum correlated to an x-intercept on the derivative. But it was the x-intercept where the derivative graph was going from negative to positive. That's where the minimum occurred. This maximum occurred when the derivative was going positive to negative. So anywhere on this graph, if you can find a place where we're going from negative to positive, that's where it would be. Well, there's only one spot, and it's right there at 6. And it really jumps out at you, and you're like, oh, right there? There is my relative min. Now I can say what it is, then I can justify my answer. And I'm going to say x is equal to 6 is a local, they use the word local, is a local minimum because f prime changes sign. And it's very important that you say from what to what, because it's changing sign at 4 too, but at 6 it's changing sign from negative to positive. Okay? So that is our answer right there. Just reading the graph. Okay? That's actually only worth a point anyway. Part B. Determine the absolute minimum value on f on the closed interval. Justify your answer. Well, I want you to pretend you just had a function and you needed to find mins. Absolute max or absolute min. What you should be thinking of is, oh, I need my critical numbers. Oh, then I have to test my critical numbers to see which one is the max and min. Well, because they want the absolute min, let's read the graph here and see what's going on. Whatever the value of the function is at 0, I want you to see what's going on between 0 and 4. Between 0 and 4, the derivative is positive, so the function is increasing the entire time until you get to 4, and this is actually a maximum on the original because we're going from positive to negative. So there's a chance that 0 is actually the smallest value because it increases to this max, then the function decreases to this min we already know about, and then it increases again to 8. So there's no way it's 8, but it could be 6, but it could also be 0. Not sure what's going on here. We could even sketch a potential of the original. We know the original is increasing. It has a flat spot, and then it keeps increasing to a max. Then it decreases to a minimum. Then it increases again. Well, this right here, that would be the 6. This right here would be the 1. There's the flat spot, and right here is where 0 is. But we can't tell. I'm just giving a maybe. I don't know if this thing went lower. I don't know where it started, so it could be 0, it could be 6. There's no way it's 8, but we actually still have to check it by rule, because you check potential critical points and your endpoints. So the only critical number candidate is 6. We know that's a max, and we know that's a flat spot. So we only have to check 6, and then 0 and 8. And you're going to see 8 comes in handy here in just a second. So you say, okay, I got to find my absolute maxes. Well, here's what I need to know. I'm curious what's going on at f of 0. Curious if I can figure that out. I also have to see if I can figure out what's going on at f of 6. And I also have to figure out what's going on at f of 8. Well, hey, I just realized f of 8 is 4. I guess we don't even have to do that one because it's done for us. So if f of 8 is 4, we just need to figure out f of 0 and f of 6. Now, we're going to have to figure this out with the fundamental theorem, but we're going to have to figure this out with values we know. So since we know 8, we're going to have to create an integral that's got 8 in it because we know it, and then we can just solve for 4. And we have all the other areas. So here we're going to go with geometry and the definition of it with the fundamental theorem. So see if this makes sense. I'm going to integrate from 0 to 8 f prime of x dx. Now I know by the fundamental theorem that that is equal to f of 8. Write that a little better. That is equal to f of 8 minus f of 0 by the fundamental theorem. Okay, now I'm trying to figure out f of 0. So I'm going to add f of 0 to the other side, subtract the integral over. I know f of 8. So this means that f of 0 is equal to f of 8 minus the integral from 0 to 8 of f prime of x dx. Okay? Now, f of 0 is what I'm figuring out. I don't know what that is. But f of 8, we already know that that's 4, minus, now it's time for geometry. So we're going to look over here and figure out what is the area under the curve from 0 to 8. Because this is f prime. So it looks like we get 2 plus 6 is 8. 8 plus 7 is 15. And then we have this 3 that is below the x-axis, so that's 12. Let me do that again. So we have the 2, the 6, and the 7. Okay, so that's 15 minus 3 is 12. So this wound up equaling 12. It looks like f of 0 is negative 8. Okay? I'm going to move this over just a little bit. And so I'm going to do my work for f of 6 right here. I'm actually going to move this over. I already knew that f of 8 was equal to 4 because that was given. Okay? So now f of 6, let's see if I can do an integral with that. I'm going to use 8 again, and I'm just going to integrate that far. And I'm going to say, well, f of 6 to f of 8 of the derivative by the fundamental theorem is going to give me f of 8 minus f of 6. Okay, so just going to do geometry again, add the f of 6 over. So f of 6 is equal to f of 8 minus this integral from 6 to 8 of f prime of x dx. Okay, so f of 6 is equal to f of 8, we know is 4, minus, let's just integrate from 6 to 8. Oh, it's 7, that's pretty easy. And we get negative 3. So we have that's negative 8, that's negative 3, and that's 4. Okay, so what is the absolute minimum value? Now the absolute minimum value, it's a y value, it's just negative 8. Now it does occur at 0, but we would just say for our conclusion, absolute minimum occurs at f of 0, which is equal to negative 8. And that's okay to put that on, and we could say the interval 0 to 8. Okay, 0 to 8, closed interval. Okay, now you could just say negatives at negative 8. The absolute minimum occurs at f of 0 equals negative 8 on 0 to 8. Got it. Okay, so that was 3 points. And there it is. Let's move on to C. Okay, so C says, on what open intervals from 0 to 8 is the graph of f both concave down and increasing? Explain your reasoning. Okay, let's do the increasing first. So I want to look at this graph down here again. If the original function in black is increasing, what's red doing? Red is, my first derivative, is above the x-axis or is positive. So if we glance up here, the places where the red is above the x-axis is where the original is increasing. Well, it's above the x-axis everywhere but here. So I'm going to just write some things down here. I'm going to write what is possible. Okay, so I'm going to say, well, I'm just going to say, well, here's what's excluded. Not the interval 4 to 6. It's not there because it's below the x-axis. Everything else is okay. All right, and in fact, sometimes students do this. You might like this approach. You actually just to help figure this out, you would say, well, let's do from 0 to 8, and let's just do 1, 2, 3, 4, 5, 6, 7, 8. And we'll just cross out what's not working. So 1, 2, 3, 4, 5, 6, 7. So 4 to 6, no good. So I'm going to say it's not there. Everything else is okay. Now the next part is, where is it increasing? And the other condition was concave down. Now look here really closely at this example. The original function was concave down where red, or the first derivative, is increasing. So wherever red is increasing, the original function is concave up. And wherever the red function is decreasing, the original function is concave down. So the question is wanting, where is it concave down? So let's just do that part. It's going to be concave down where the derivative is decreasing. So let's take a look here. Where's the derivative decreasing? Well, it's decreasing between 0 and 1. Okay? It's increasing from 1 to 3. So there it's increasing, so it can't be from 1 to 3. I'm going to cross those out. It's increasing. Okay, it's decreasing from 3 to 4. That's okay. It's decreasing, well, who cares from 4 to 6? It doesn't really matter, does it? Because this was below the x-axis. And then we're increasing here, so we're no good here. Okay, so by elimination, it looks like the only places where red is doing two things, it's above the x-axis and it's decreasing. So it's above the x-axis and decreasing from 0 to 1 and from 3 to 4. Everywhere else, something's not okay with it. Okay, so I'm going to, now that I've got this, I'm going to tweak my answer here and say, the graph of f is, and I'm going to, on here, I'm going to put my interval here, 0 to 1 and 3 to 4, just to remind myself. But I'm going to erase that to get rid of the, so I have the space here. Okay. So the graph of f is concave down is the restriction. It is concave down and increasing. On the interval, or intervals. All right, now the first one was from 0 to 1. Okay, so we can say, we could put it in interval notation, or we can write an inequality. I'm going to do an inequality. I'm just going to say 0 is less than x is less than 1 on that interval. And it was 3 less than x less than 4. Okay, now the reason I'm not including those endpoints there, especially on 1, is that it's actually 0 right there. And so at the endpoint, it's not continuing to decrease there. And on 3 and 4, it's the same thing. At 4, it's actually 0, and there it's the peak. They might actually give you points there for having it anyway. But the reason is the graph of f is concave down and increasing on these intervals because, and here's where we have to make sure we read this correctly here, because f prime is doing two things. It is both, now remember, to be increasing, the original function is increasing, f prime had to be positive. F prime is both positive, that was the first restriction, but the other thing it had to be doing was, to have the concave down part, it had to be decreasing. Okay? And we'll get rid of that. There is part C. Okay? Now part D actually overlaps a little bit with the function build idea. I think I have enough room to sneak D in right here without having to erase these graphs, which might come in handy for you as you're reviewing. So I think we'll do that. All right, and here we go. So I'm going to sneak part D in right here. All right, here's what D says. D says the function g, so now they give us a new function. I'll do that, move that up here just a little bit. So here is part D. It says the function g is defined as f, it's actually g of x. The new function g is defined as g of x is equal to f of x, the entire function cubed. Okay? Now they tell us that f of 3 is negative 5/2, and they want us to find the slope of the tangent to the graph at g at 3. Slope of the tangent, slope of the tangent, slope of the tangent. You should know definitely the slope of a tangent is a derivative. So the slope of the tangent is the derivative of g. So I'm going to write here, well, they want the slope of the tangent. Well, the slope of the tangent is equal to the g prime. It's the derivative of g. So g is defined as this thing, so what we have to do is a little mini chain rule here. So 3 times f of x squared, okay, so there's the outside, times the derivative of the inside here, which would just be f prime of x. So there's the formula for the slope of the tangent, and now we just have to evaluate it. We have to evaluate it at 3. So now I'm just going to say, well, I need to put 3 in here. So g prime of 3 is equal to 3 times whatever f of 3 is, and I need to square that, times the derivative at 3. Okay, so moving this over here a little bit. So g prime of 3 equals 3 times, I need to know what f of 3 is, and then I need to square it. If only I knew what f of 3 was. Well, they gave it to us in the question. It's negative 5/2. So that was pretty easy. Negative 5/2 times, and now I need the derivative at 3. Well, here's the graph of the derivative, and I sure hope 3 gives us a nice place. 3, there it is, it's right at the peak, it's 4. So that was a combination. This was a little bit of function build, a little bit of derivative, chain rule, and then just, reading the problem. So let's see what we get here if we can simplify this. So g prime of 3 is 5/2 squared, that's going to be 25 over 4. So I've got 3 times 25 over 4 times 4. So it looks like those 4's cancel, and my final answer is g prime of 3 is equal to 75. Okay? So, there it is, another derivative graph, and you can't review this enough right here. Make sure you guys have this, and make sure you have that available. Always be looking that over, the relationship of your derivative graphs, because these are great non-calculator questions. So again, on A, just reading the graph, knowing your maxes and mins occur at x-intercepts of your derivative. Make sure you know what a kiss means. A kiss means a flat spot, but they just wanted the local min. Then evaluating by the fundamental theorem, picking apart what we had to do there to find the absolute minimum, which occurred here at -8, or is -8, occurred at 0. Then part C was reading the graph about concavity and increasing by reading the derivative. And then part D, little derivative function build, actually one little part of it was kind of a potpourri. Okay, so there it is, question number 4. The year is 2013, derivative graph. All right, thanks for watching. We'll see you next time.